For 40 years, theoretical computer science has struggled to make progress on hash tables, a basic data structure that underpins much of modern computing. Whenever a database pulls up a customer record, a web browser checks a saved password, or a router sends data, a hash table is probably at work. Think of these structures as the internet's filing cabinets, built for speed. Trouble starts when the cabinet fills up. For decades, computer scientists believed that as a hash table gets close to full, its performance must drop. If you try to fill a storage system to 99%, probability says you'll pay with slower speeds. Instead of quick lookups, you end up searching through a mess. This belief was codified in 1985 by Andrew Yao. He is a titan in the field and a recipient of the Turing Award, which is the Nobel Prize of Computing. Yao published a seminal analysis that seemed to set a speed limit on how efficiently a dense hash table could operate. This conclusion became a foundation of the field for 40 years, until Andrew Krapivin came along. Andrew, at just 21-year-old undergraduate student at Rutgers University, has written a paper that has demolished this 40-year-old conjecture. In fact, Andrew did not even know the conjecture existed. He was simply working on a side project about memory compression, and he needed a tool that did not exist. He sat alone late at night, staring at a research paper about a concept called tiny pointers. He started tinkering with the math just for fun. He wanted to see if he could make a computer memory system that was just a little bit more efficient. Little did he realize that he was stepping into a problem that had stumped top computer scientists for 40 years. Without realizing it, he has overturned a long-held belief and shown that Yao's speed limit could be broken. To see why Andrew's discovery matters, let's look at one of computing's biggest challenges: how to find data quickly and efficiently. Picture a library with millions of books. If you want The Great Gatsby and there's no sorting system, you'd have to check every shelf until you find it. In computer science, this is called linear time. As the library grows, so does the search time. For computers that need to work at lightning speed, linear time just isn't good enough. Hash tables solve this problem. They're like a magic trick that lets you find the needle without digging through the hay. This trick uses a mathematical formula called a hash function. You put in the data you want to store, like the title, The Great Gatsby, and the function gives you a number. Let's say it gives you 42. That number is an address, telling the computer to put The Great Gatsby on shelf 42, slot 1. When you want the book later, you don't have to search. Just put the title back into the function, get 42 again, and go straight to that spot. The book is waiting for you. In a perfect world, this process is instant. It takes the same amount of time whether there are 10 books or 10 trillion. That's why hash tables are everywhere. They promise instant access. But the universe is rarely ideal. The friction enters the system, but things aren't always perfect. Hash functions are blunt tools. They map lots of possible data onto a limited number of slots. Sooner or later, two pieces of data will end up fighting for the same spot assigns it to shelf 42. You now have a collision. Two books cannot occupy the same physical space. The system must decide what to do. Engineers have two main ways to handle this. The first is called chaining. Here, shelf 42 acts like a bucket. You just pile all the books that land there into it. If more books map to that slot, they go in too. It's simple, but messy. It needs extra memory to track the overflow, and the computer has to jump around to find the scattered data, which slows things down. The second approach is more elegant but riskier. It's called open addressing. In an open addressing system, every slot holds exactly one item. There are no buckets. If shelf 42 already has The Great Gatsby, the system has to find another spot for Moby Dick. It checks shelf 43, then 44, and keeps going until it finds an empty slot's a critical vulnerability. As the table fills up, the collisions become more frequent. The empty spaces become rarer. The hunt for a free slot takes longer. This is the phenomenon that Andrew Yao analyzed 40 years ago. It is known as the problem of the full parking lot. Everyone knows what it's like to drive into a parking lot that's only 10% full. You find a spot right away and park with no trouble. Now imagine a parking lot that is 99% full. There are 1,000 spaces, and 990 of them are occupied. You drive in, you cannot find a spot. You spend 10 minutes driving past occupied spots, that one elusive opening. In a hash table, this search is called probing. As the table gets closer to full, the number of probes needed to find a spot goes way up. In 1985, Andrew Yao wanted to quantify exactly how bad this problem could get. He focused on the extreme regime. He looked at tables that were nearly full. He used a variable, which we will call x, to represent the inverse of the free space. If the table is 99% full, 1% is free. The variable x is 100. If the table is 99.9% full, 1/10 of 1% is free. The variable x is 1,000. Yao studied how greedy algorithms work. These algorithms grab the first empty slot they find when storing data. They don't wait or look ahead. They just take the first available spot. Yao argued that for any greedy strategy, you are at the mercy of probability. If only 1 in 1,000 slots is empty, you will, on average, have to check 1,000 slots to find one. The work required to insert a new item grows linearly with x. This means that if you double the density of the table, you double the work. If you increase the density by a factor of 10, the system slows down by a factor of 10. Yao went further. He formulated a conjecture about the worst-case scenario. He proposed that among all possible strategies for placing data in this restrictive model, the best you could possibly do was to mimic pure randomness. This is known as uniform hashing. The idea is that if you scatter data randomly, you avoid creating patterns. Yao's conjecture implied that randomness was the ceiling of performance. You could not do better than chaos. This idea became widely accepted. It meant you had to choose a fast hash table or a full one, but not both. To keep things speedy, you had to leave a lot of memory empty, wasting valuable space just to avoid slowdowns. Andrew Krapivin came to Rutgers with many interests and was double majoring in math and computer science. He also likes to browse research papers outside his classes. In fall 2021, he found a paper called Tiny Pointers. The paper was co-authored by Martine Farah-Colton, a professor at Rutgers who would later become Andrew's mentor. The paper tackled a problem of compression. In a computer, a pointer is just an address. It is the number that tells the machine where a piece of data lives. In massive systems with billions of data points, these addresses can become very large numbers. Large numbers take up space. The paper proposed a clever way to shrink these pointers to save memory. Andrew became fascinated by how the problem worked. He wondered if he could make the compression even better. Could he make the pointers even smaller? But there was a catch. To use a very small pointer, you need to know exactly where the data is. You cannot afford to have the data scattered across a vast, sparse landscape. You need the data to be packed tightly together. A small pointer implies a small address space. This led Andrew to hash tables. To make his tiny pointer idea work, he needed a hash table that could be almost completely full and still run quickly. The usual methods, such as linear probing, quadratic probing, and the standard greedy algorithms, just didn't cut it when he looked into them. They kept failing his most important test. Once the data structure started filling up, they'd inevitably choke, which confirmed the bottleneck Yao had warned about. But Andrew didn't know about Yao or his famous theory. He just saw that the usual methods failed, so he set out to design his own way to insert data. He started to question whether greedy algorithms were really the best approach. In a standard hash table, if the algorithm hashes a book to slot 42 and slot 42 is empty, it puts the book there. Why would it not? It seems foolish to skip an empty space. It seems inefficient to drive past a parking spot near the front of the store. But Andrew saw that greedy choices have hidden downsides. When algorithms always take the first open spot, they create clusters. Imagine 10 slots in a row. If slots 1, 2, and 3 are filled, they form a block. If a new item lands at slot 2, it's taken, so it checks slot 3, then slot 4, and ends up there. Now the block is even longer. These clusters act like gravity wells. The bigger they get, the more likely they are to catch new items. The clusters merge, they grow, they form long, continuous runs of occupied data. These runs are the traffic jams of the hash table. When the table is 99% full, these runs can become massive. A new item might have to travel thousands of slots to get to the other side of the jam. Andrew wondered what would happen if the algorithm were less desperate. What if it exercised a little self-control? He developed a strategy that he eventually called elastic hashing. The idea was counterintuitive. When the algorithm tries to insert an item, it probes a sequence of spots. It might find an empty spot early in the sequence, but instead of taking it, the algorithm might decide to skip it. It might leave that spot empty on purpose. Why would you leave a spot empty? Because an empty spot acts like a fire break. By strategically leaving empty spaces in the middle of dense regions, the algorithm prevents the clusters from merging. It keeps the traffic jams short. It sacrifices the immediate convenience of the first available spot to preserve the long-term health of the entire structure. Andrew started modeling his idea, working through the logic on whiteboards and running simulations. He wanted to see how performance changed as the table filled up. He expected some improvement, but he didn't expect to overturn the established rules. When he looked at the worst-case scenarios for elastic hashing, he saw that the link between how full the table was and its speed had changed. It wasn't linear anymore. It didn't depend directly on x. Performance now followed a logarithmic curve. The time needed to insert an item grew with the square of the logarithm of x. To the layperson, the difference between x and the logarithm of x squared might seem like a minor detail of notation. In the world of large numbers, it is the difference between a mountain and a molehill. Let us return to the parking lot. Suppose the lot is so full that x is 1 million. There are 1 million occupied spots for every one free spot. Under Yao's linear prediction, finding a spot would require, in the worst case, 1 million checks. The system would be unusable. Under Andrew's logarithmic model, you calculate the logarithm of 1 million, which is roughly 20. You square 20, you get 400. 1 million versus 400. That is the scale of the breakthrough. Andrew had designed a system that could be filled to the absolute brim, 99.9999% full, and still function with the snap and speed of a nearly empty system. He realized he'd found something big. He gathered his notes and went to see Professor Farrokh Colton. Farrokh Colton has spent 32 years at Rutgers and is a veteran of the algorithmic trenches. When Andrew laid out his claim, a hash table that defied the linear speed limit, Farrokh Colton was skeptical. Andrew had to be missing something since conjecture had stood out for 40 years. The smartest minds in the world had looked at it. If there were a simple trick like skipping a spot, surely someone would have found it by now. But Farrokh Colton also knew Andrew was different. He'd seen him master graduate-level ideas and knew he had the talent to back up his intuition. So he did not dismiss the boy, he invited him to prove it. Farrokh Colton brought in a third mind to help verify the work. He contacted William Kussmaul, a theoretical computer scientist at Carnegie Mellon University. Kussmaul is a prodigy in his own right, a former Goldwater scholar who specializes in the granular details of data structures. Kussmaul reviewed the manuscript, studied how elastic hashing worked, followed the logic of the fire breaks, and checked the probability calculations. Then it hit him. Kussmaul told Andrew, "You didn't just come up with a cool hash table. You've actually completely wiped out a 40-year-old conjecture." The three researchers formed a team. They spent the next year rigorously formalizing the mathematics. They had to prove that Andrew's simulation was not a fluke. They had to construct a bulletproof logical argument that showed why the log x squared bound held true for every possible case. In their paper, Optimal Bounds for Open Addressing Without Reordering, they presented the proof. They showed that by giving up greedy algorithms, you could avoid the linear slowdown. But as they dug deeper into the properties of non-greedy hashing, they uncovered a second surprise. This one was even more shocking than the first. Yao's 1985 paper had not just predicted the worst-case scenario, it had also established a limit for the average time to find data. Yao proved that for any greedy algorithm, the average search time must grow logarithmically as the table fills up. Even in the best greedy system, a full table is slower than an empty one. This seems like common sense. A crowded room is harder to move through than an empty one. More density means more friction. But Andrew's algorithm is not greedy, and because it broke the greedy rule, the team found it could also break the average time barrier. They discovered a variant of their strategy where the average search time does not grow at all, it remains constant. This is a statement that defies physical intuition. It implies that you can have a memory bank that is effectively 100% full, and yet, on average, you can find a piece of data just as quickly as if the bank were empty. It's like a parking lot that's packed full, but every driver still finds a spot in 2 minutes every time. How is this possible? It all comes down to managing disorder perfectly. In a greedy system, the randomness creates clumps. Some parts of the table are empty, some are solid blocks. You waste time traversing the blocks. In Andrew's system, the algorithm manages the empty spaces so aggressively that they are distributed with perfect evenness. You are never far from a hole. The fire breaks are spaced out so regularly that the probe sequence never has to travel far to find one. The team proved that this constant time performance was achievable with high probability. They had found a way to decouple density from drag. The team did one last thing. They proved that they could not go any further. In mathematics, it is one thing to beat a record. It is another thing to prove that the record can never be beaten again. Andrew, Farah, Colton, and Kuzmal derived a lower bound for the problem. They proved mathematically that for this class of hash tables, the worst-case time of log x squared is the absolute floor. There is no algorithm, discovered or undiscovered, that can do better. Andrew had not just improved the state of the art, he had hit the bedrock of the problem. He had found the optimal solution. The paper came out in January 2025 and made waves in theoretical computer science. Guy Blalock, a professor at Carnegie Mellon, called the result beautiful. It was the kind of clear, final answer mathematicians dream of. Sapir Asadi, a professor at the University of Waterloo, pointed out how lucky the timing was. "We could have gone another 40 years, he said, still believing in the linear wall. It took a mix of curiosity and not knowing the old rules to break through." Andrew Krapivin surprised himself when he overturned a famous conjecture, one put forward by a Turing Award winner. He says the breakthrough came down to a few things. Sure, he was just having fun and playing around with the problem, but he also credits the solid support he got from his mentors and his family. The implications of this work will take years to fully filter through the ecosystem of computing. Today, computing is moving to the edge. We're putting powerful AI on phones, watches, and tiny sensors in factories. In these devices, memory is precious, every bit matters. Before this work, engineers would leave 20 or 30% of the memory empty just to keep the system from slowing down. That is a massive amount of wasted space. Andrew's work suggests that we can run these systems hotter. We can push them to 99% capacity, and with the right non-greedy algorithms, we can keep them running at top speed. This could lead to faster databases, more efficient caches, and leaner. As for Andrew, he finished his undergraduate studies in 2024 and is currently an incoming PhD student at Carnegie Mellon University, one of the most reputed computer science programs globally. He was named a 2024 Siebel Scholar, an honor recognizing the world's most talented graduate students in computer science, business, and bioengineering. His paper, Optimal Bounds for Open Addressing Without Reordering, was accepted in the 65th Annual Symposium on Foundations of Computer Science, one of the most prestigious conferences in theoretical computer science, and covered in Quanta magazine's biggest computer science breakthroughs for 2025. He has interned with Jane Street, one of Wall Street's most successful and exclusive quantitative hedge funds. For Andrew, the sky is the limit.